So this week we're going to look at rational numbers. So I'll show you what that means. We're going to order them. We're going to look at using the number line. We're going to talk about absolute value. So let me share some problems with you. We'll go through some of these together. All right, so first of all, I want you to know the word integer. An integer is a whole number, which is like a counting number, 1, 2, 3, 4, 5. It's all whole numbers, their opposites, and the number 0. So all of these are examples of integers. 2, -2, 5, -5, 7, -7, 0. So anyway, integers do not include decimals and fractions. However, now I'm introducing the word rational number. A rational number is any number you can write in fraction form. So all integers are rational numbers because you can write 2 as a fraction, 2/1, or -2, -2/1, 5 would be 5/1. So rational numbers include all integers plus all fractions, as long as it doesn't have a symbol as part of the fraction. And then decimals that terminate, which means to stop, like 0.5 or 0.25, or numbers that repeat in a pattern. So like this one right here, we have a decimal that doesn't terminate, but it repeats 0.3333. Okay, so all of these are examples of rational numbers. 5, 1/2, -4. Those 5 and -4 are integers, the number 0. 0.56 is a terminating decimal. The number 3, 0.3333, etc. 7/5. And even if you have, let's see, you have 2 numbers that repeat over in that pattern, that is also a rational number because you can write repeating decimals as fractions. Now, if it's not a rational number, that means that the number would be irrational, like the symbol pi. A lot of you have seen that symbol and know that it's called pi. That is an irrational number. That's a number that cannot be written in fraction form, which means it's a decimal that goes on and on and on forever and doesn't repeat in any pattern. All right, like I said, rational numbers can be written as fractions. Now, as we go through, as we get higher in 7th grade and go into 8th grade, we'll start talking about squares and square roots, perfect squares. So since 5 squared is 25, that means the square root of 25 is 5. So if you have a square root of a perfect square like 25, that's a rational number because the square root of 25 is an integer. It's 5. The square root of 100 is 10, which is a rational number. The square root of 9 is 3, which is a rational number. The square root of 64 is 8. So anytime you are asked for the square root of a perfect square, those are all rational. But if you have a number that's not a perfect square, like 2, 5, 20, 27, 50, there's no number times itself that equals 2. There's no number times itself that equals 5, so on and so forth. So if you're ever asked what is the square root of a non-perfect square, that is an irrational number. It's a decimal, it goes on and on forever, and it doesn't repeat in any pattern. And then, like I already said earlier, pi, that symbol that has to do with the circumference of a circle divided by its diameter, we always get that number pi that we estimate to be about 3.14. Pi is irrational. All right, so there's 2 vocabulary terms for you, integers and rational numbers. Now, when you order rational numbers, you want the easiest way to order them, meaning list them from least to greatest, is to make them all look the same. So you can either make them all look like fractions. The problem with that is that you would have to make them all have common denominators, which can be a lot of work. Or the easiest thing, my suggestion is to always make them decimals if you need to. So for example, look at the first one, 9/4. So this is -9. So first of all, before I look at letter A, let's just talk about a number line. So you guys are familiar with number lines. You've been using them for years. Mostly you've dealt with the positive side of number lines, but now we're going into the negative side of number lines. But one thing that is always true, the farther right you go on a number line, the numbers get bigger and bigger and bigger. So if a number is to the left of another number, that means they're small, it's smaller than the number to its right. The farther left you go on a number line, the numbers get smaller. The further right you go on a number line, the numbers get larger. So when you place them on a number, when you place numbers on a number line, you can order them easily because they're in order from left to right on a number line, least to biggest. All right, so let's turn 9/4 into a decimal. So we're going to put top dog in the house, right? So we're going to put 9 in the house, 4 outside the house. 4 will go into 9 twice. Subtract. 4 won't go into 1, so I'm going to add a decimal. Bring my decimal straight up. 4 will go into 10 twice. A remainder of 2. No, wait, this isn't right. I'm sorry. Yes, it is. I don't know what I was thinking. I'm sorry. All right. So anyway, so 9/4 is equal to negative 2.25. Okay. So we're going to write them out as decimals. All right. Now we're going to do 3 halves, 3 over 2. So 2 will go into 3 one time with 1 left over. So we're going to add a decimal and a 0. Bring your decimal straight up. 2 will go into 10 5 times. So 3 halves is positive 1.5. All right, this one's already in decimal form, 1.25. Then 1/4 as a decimal. If we divide 1 by 4, add a decimal. 4 will go into 10 twice. Bring down our 2 and our 0. So this is negative 2.25. This is negative 2.75, right? Then, of course, we have 2, 0, 2, and 0.56. All right, so let me get rid of a lot of this stuff here. Get rid of this. All right, let me get rid of all this stuff. Okay, so now let's put these in the on the number line where they go. Let's use blue. All right, negative 2.25. So here's negative 2, here's negative 3. This would be negative 2.5. So negative 2.25 is right here, negative 9/4. Oh, this pen hates nines. I don't know why. All right, then the next one is 1.5. So here's 1, here's 2. So here would be 3 halves, positive 3 halves. Here we have 1.2. So this is like $1.50, and this is $1.25. So right here, I'm going to put 1.25. All right, now we're going to do negative 2 and 1/4. Oh my gosh, I have it on there twice, don't I? These are equivalent. I didn't even notice that. All right, so this is the same as this. Sorry about that. I don't know what I was thinking earlier. I was thinking I wrote a different number and I meant to have a different outcome, but it's totally fine. All right, so now here we have negative 2.75. So here's negative 2, here's negative 3. So here is going to be about where negative 2.75 is. And then, of course, we have 0, we have 2, and we have 0.56, which is a little bit more than 0.5, isn't it? So 0.56. All right, so what is our smallest number? In other words, which one is farthest left? Well, farthest left is this one right here. So I'm going to order these. That's the smallest one is negative 2.75. So I'm done with this one. All right, what's next? Next, we have negative 2.25. So we're going to write it back in its original form. Negative 9/4 is next. All right, moving to the right, 0. We don't have any more negative numbers because I wrote the same one twice. That's 0. And then to the right, the next one is 0.56. All right, and then we have 1.25. So it'd help if I mark these off so I know I'm done with them. And our biggest number on the board, oh, whoops, I marked out a 2, but we didn't use it. I don't know what my problem is, you guys. 3 halves, and finally the biggest number is 2. Okay, so that's a little bit of work, isn't it? That's okay. All right, I'm gonna get rid of all this because I know there's another problem for us to look at. I'm gonna erase all this. Let's look at letter B. We have a lot less numbers, don't we? All right, so let's turn 1/5 into a decimal. So I'm just gonna make a decimal. So 5 goes into 10 2 times. So this is 0.2. And then our only other decimal is -0.5, correct? So we're going to put 0.2. So this is 0, this is 1. So this would be about where 1/5 is. And then -1.4, here's -1, here's -2. So it's not quite -1.5. So -1.4. And then our number 3 is up here. And then -0.5. So -1/2. All right, so from least to greatest, we have -1.4 is our smallest. That's that one. Next one up is -1/2. And then our positive numbers go next. So then I have +1/5. And finally, our biggest number is 3. So the farther left you go on a number line, the numbers are smaller. The farther right you go, the numbers are bigger, right? So then when we compare these, we would want to think, okay, which one is farthest left on a number line, right? So here's -2. -5 halves is going to be -2.5. So here's -2, -3, -10 would be way down here. All right, so which ones, so you would say that -2 is to the right of or to the left of -5 halves? Well, since -5 halves is to the left of -2, you would say -2 is greater than. I lost my pen. I'm trying to change colors. So -2 is greater than because it's to the right of -2.5. All right, so here's -2 again. Here would be -4. Obviously, this is not drawn to scale because my 10 is too close. So this would be -4.5. So which one is farthest right? Well, since -2 is to the right of -4.5, -2 is greater than. So if think about this as temperatures, -2 is going to be warmer than -4.5, isn't it? What about this one? Which is the coldest temperature? Well, -10 is to the left of -4, isn't it? So you would say -10 is less than -4. All right, what about -1 and -2/3? Well, -2/3 is going to be 0.6666 repeating because we're always going to get a remainder of 2. Right, so -1 would be about right here, and -2/3 is going to be here. So since -1 is farthest left, -1 is less than -2/3. So if you have 2 negative numbers, the answer is going to be the opposite than if they were both positive numbers. Do you understand that? So look at this one. Wouldn't +10 be greater than +4? Well, since they're both negative, it's the opposite. Isn't 1 going to be greater than 0.6666? Then since they're both negative, it's the opposite of that. All right, now you don't have to turn them into decimals if they have common denominators. So then all you have to do is compare the numerators. Now let's think about it if they were positive numbers. Wouldn't 4/6 be greater than 1/6 if they were both positive? It would be. So since they're negative, they're both negatives, it's going to be the opposite. Negative 4/6 is going to be farther left than negative 1/6. Okay, hopefully that helps a little. All right, now the next term, and probably, I think you guys have used it in class before, so you probably already know what absolute value means, but absolute value is always saying how far from zero these numbers are on the number line. And in distance, you never use a negative number. So for example, if your family went to Walmart and it was east of your house, let's say you drove 3 miles to Walmart that was east of your house, but then you had to go to the grocery store and it was 6 miles in the opposite direction, you wouldn't say we went 3 miles east and then negative 6 miles. You wouldn't say that because distance on your odometer on a car is always going to go forward, whether you're in reverse or turn the opposite direction. So distance is always a positive number. So this is showing us here that an absolute value are these like long straight lines. The absolute value of -4 is 4 spaces from 0. And how far is 4 from 0? Well, the absolute value of +4 is also +4 because both of these numbers are 4 spaces from 0. So that's what I mean by it's always a positive number. So let's look at letter A. What is the absolute value of 6? The absolute value of 6 is 6 because 6 is 6 spaces from 0. What about the absolute value of -6? How many spaces from 0 is -6? +6. The absolute value of -5 is +5. And the absolute value of 8 is 8. And that's it, guys. Absolute value means distance, and distance is always given as a positive number. Now the word additive inverse, you could call them opposite numbers. Also, you can say it's a pair of numbers that have a sum of 0. So what would be opposite numbers, or numbers that if we add them together, we get 0? Well, let's say you did some chores and you made $10, but then you went to the store and you spent $10. How much money do you have? 0. So gaining 10 and losing 10 gives you a sum of 0. So 10 and -10 are opposite numbers. What about 2? What's the opposite of 2? -2. What's the opposite of -40? +40. What's the opposite of 100? -100. You got it. So you guys understand opposite numbers or numbers that are additive inverses of one another. All right, look at these real world examples. Which examples can be combined to make 0? I spent $10 on candy, then spent another $10 on a book. Would that be a sum of 0? I made $22 working, but then I spent $22 on Spotify. How much money do I have? I rode my bike to the stop sign and then turned around and went right back home. And then the last one, a plane takes off, circles the airport, and then lands at the same airport. All right, so all of these are real world examples that combine to make 0 except the top one, right? So if I made $22, but then I spent $22, I have 0. If I rode my bike to the stop sign and then I turned around and came back home, then how far from my home am I? I'm exactly where I started. Now you would say that you put positive miles on your bike, but we're just wanting examples that you would combine to get the same place that from whence you started, right? So all of these are good examples except the first one. On the first example, we just spent $20. So that's what it says. We spent $20. All right, so you're going to look at using a number to model addition and subtraction. So the first number tells you where you're starting, and then the second number tells you what to do from there. So if we started at 0 and Janice owes her dad $9, well, if you owe someone $9, you're $9 in debt. So Janice owes her dad $9 and then she pays him back $4. So what does that tell you? It tells us that Janice is still in debt $5. DEBT. She's still in debt $5. She owed her dad, she owed her dad $9 and paid him $4. She still owes him $5. All right, Jackie walked 5 blocks east. So here's where Jackie started. She walked 5 blocks east. And then from there, she walked 5 blocks west. So she is where she started. So that's using a number line to model that. All right, so we can use number lines to model addition and subtraction problems. So look over here. It says, if you see a plus, it means to go right. But if you see a minus, it means to go left. So from 0, we're going to go to +5 right here. And then this says we're going to go left 7. So from 5, we're going to go left 7. And that means we would stop on -2. Well, this looks like a different problem, but we go right 5. And then it tells us to go right, but immediately after that, it says, actually, you're going to turn around and go left 7. So that's why both of these problems gives us a -2 as an answer. All right, let's look at this one. This says start at 0, go left 2. And then this says we're going to continue to go left 6 more. And where do we land? We land on -8. All right, this one, let me erase what we just did. This one tells us to go left 6 to start with, left 6. And then this says, actually, we're going to go right 8. So what do we land on? We land on +2. So you guys are going to look at number lines to model addition and subtraction and other real world examples. Oh, that's it. All right, you guys. So I hope that helped. So the lessons this week are pretty good, pretty simple, not too difficult. And then on Friday, you have a Delta Math practice to sum it all up. Okay. All right. So I think we're meeting. Let's see, we're Zooming Friday at 9 o'clock. So hopefully I will see you guys then. So make sure if you have any questions, bring them to our meeting or let me know before then. Have a good day.